Have you ever found yourself wondering if the effort you put into exercising one side of your body could somehow almost magically benefit the other?
Yeah, like if you intensely stretch your right leg, does your left leg kind of secretly get a flexibility boost too?
Exactly. It sounds almost too good to be true, right? But it's a really fascinating question.
It is.
And today, we're going to dive deep into a recent piece of research that sheds surprising light on exactly this: how dynamic stretching impacts our flexibility, our muscle properties,
Uh-huh.
not just in the limb we're actively working on, but quite remarkably in the other limb as well.
That contralateral effect, yeah.
Our mission today, then, is to unpack this intriguing idea, this interconnectedness within our bodies.
Okay.
We'll be focusing on a study titled Effect of 12-Week Dynamic Stretching of Ankle Plantar Flexors on Joint Flexibility and Musculoskeletal Properties in the Contralateral Muscle.
Right. Quite a mouthful, but important work.
It is.
Okay.
This research was done by Naoki Ikeda, Kazuya Hiratsuka, and Tadao Isaka. And it was published in the Journal of Sports Science and Medicine, online, June 1st, 2025.
A well-respected journal.
Absolutely. And this isn't just about ankles, really. It's about understanding how our entire physical system communicates.
How it all connects.
Yeah. Okay, let's unpack this and see what these researchers truly discovered about our body's remarkable, sometimes hidden connections.
Let's do it.
So to really get to grips with this, maybe let's start with the basics. Dynamic stretching itself. What exactly are we talking about?
Good idea. So think about those active warm-ups you often see athletes doing. Arm circles, leg swings, torso twists.
Right, the moving stretches.
Exactly. That's dynamic stretching. It involves moving a joint through its full range of motion. You're not holding a position.
Okay.
Instead, you're repeatedly lengthening and shortening the muscles, usually in a controlled, sort of fluid way.
Rhythmic sometimes, like 1 or 2 movements per second.
Often, yeah.
Right.
Around 1 to 1.5 hertz, which is about that frequency. And it's really distinct from static stretching.
Right, where you just hold a stretch for, say, 30 seconds, feeling that pull.
Precisely. Dynamic stretching has become, well, really the go-to warm-up for many sports.
Why is that, mainly?
Because it primes the body for movement, gets the blood flowing, increases muscle temperature, and crucially, it does this without typically hindering performance, like reducing strength or power right before you need it.
Which static stretching can sometimes do if you do it right before intense activity, yeah.
It can, potentially. So dynamic stretching avoids that downside while still improving flexibility for the upcoming activity.
Makes sense.
But while it's widely favored for those immediate benefits, there's been a bit of a gap in our understanding.
Okay, like what?
Well, what about the long-term effects? If you do this consistently, say over several weeks, how does that influence things?
Not just on the day, but cumulatively.
Exactly. And specifically, how does it affect not just the leg you're stretching, but also the contralateral limb, the one on the other side?
Ah, back to that crossbody effect.
Right. In terms of joint flexibility, sure. But also the actual elastic properties of the muscles themselves. Does the muscle tissue change?
Interesting distinction.
And this study also aimed to clarify another point that's been a bit debated. Can dynamic stretching actually improve muscle functions like force or power over time?
Like, could it make you stronger?
Potentially. Previous research has shown sort of mixed results there, so a long-term study was really needed.
Gotcha.
So the precise goal of this work by Ikeda and his colleagues was to examine the effects of a 12-week dynamic stretching program. They focused specifically on the ankle plantar flexors.
Your calf muscle.
Your calf muscles, yeah. And they looked at joint flexibility, muscle strength, and those elastic properties in both legs, the one being stretched and the one acting as the control.
Okay, that's a very clear and ambitious goal, really dissecting that long-term bilateral impact. So how did they set it up? Who were the participants?
Right, the participants, they recruited 18 healthy young adults, a mix of males and females, 12 men, 6 women, all aged between 18 and 24.
So college age, roughly.
Pretty much.
Yeah.
And an important point, these weren't sedentary people. They were already doing some regular exercise, at least once a week.
Okay, so relevant to an active population.
Definitely. And to keep things clean, minimize confounding variables, they were strictly told not to start any new lower body training during the 12 weeks.
Ah, so the only new thing was the stretching program for one leg.
Precisely. Really trying to isolate the effect of that dynamic stretching.
That's a well-defined group. Now, you mentioned one leg was stretched, the other was a control. That sounds like a clever design.
It really is. It's called the within subjects design, and it's quite robust.
How did it work exactly?
For each person, one leg was randomly assigned to get the dynamic stretching intervention. The other leg, it just served as the non-intervention control.
So, comparing left versus right leg within the same person.
Exactly. It minimizes the influence of individual differences in genetics, diet, overall fitness, you name it. Any difference between the legs is much more likely due to the stretching itself.
Clever. Okay, so what did the actual stretching involve? It was 12 weeks, 3 days a week, you said, focused on the calf.
That's right. It was quite specific and, frankly, demanding. 3 days weekly for the full 12 weeks. And they did 2 distinct types of dynamic stretches for those ankle plantar flexors.
Okay, what were they?
The first was flexion and extension, pointing the foot up and down, but in a narrow range of motion.
Yeah.
And quite fast, at 1.5 hertz.
So, quick little pulses.
Kind of, yeah.
Yeah.
Quick, controlled up and down movements. The second type was also flexion and extension, but through a wide range of motion. Here, they went slower, about 1 hertz.
Once per second.
Right. And participants were instructed to really raise their heels high, getting up to about a 45-degree angle at the ankle, pushing that full range.
So, one fast and short, one slower and bigger.
You got it. And each session wasn't trivial. They did 5 sets of 60 seconds for each type of stretch,
Wow, okay.
with a 30-second rest between sets. So that's quite a bit of stretching volume each session.
Definitely. And what about intensity? Were they just going through the motions?
No, they specified that too. They called it discomfort intensity. They used a simple 1 to 5 visual scale, and participants aimed for a 4.
So, definitely feeling it. Pushing boundaries a bit, but safely.
Exactly. Making sure the stimulus was actually significant enough to potentially cause an adaptation.
Wow, that is a seriously thorough and well-controlled routine over 3 months. Really shows they wanted solid answers.
Absolutely.
And to measure the impact, they needed equally precise tools, right? What exactly did they measure?
They focused on 3 main things to get a full picture.
Yeah.
First, ankle flexibility itself. They measured dorsiflexion range of motion, or DFROM.
Which is basically how far you can bend your foot upwards towards your shin.
Exactly. A direct measure of ankle joint mobility. Very standard.
Okay, number 1, flexibility. What else?
Second, they looked at the physical properties of the muscle tissue, specifically muscle stiffness.
How rigid the muscle is?
Kinda, yeah, how resistant it is to being stretched. They looked at the medial gastrocnemius, one of your main calf muscles.
And how do you even measure that?
They use a cool technique called shear wave elastography. Basically, they send tiny, harmless sound waves through the muscle and measure how fast those waves travel. Stiffer tissue transmits waves faster. It gives you a quantitative measure of the muscle's physical stiffness or elasticity.
Wow, okay, so directly assessing the tissue's physical property.
Exactly. Not just how far it can move, but how stiff it is.
Got it. Flexibility, stiffness. What was the third area?
The third was ankle plantar flexion strength.
Okay.
How strong the calf muscles are when pointing the foot downwards.
Okay. Did they just, like, lift weights?
More sophisticated than that, they used 2 metrics. One was the rate of torque development, or RTD.
How quickly you can produce force.
Precisely.
Yeah.
Explosive strength, in a way. And the other was isokinetic muscle strength, which measures your peak force production through a range of motion at a constant speed.
So looking at both how fast and how much force they could generate.
Exactly. A pretty comprehensive look at strength qualities.
That really is a full picture. Flexibility, muscle properties, and functional strength. Okay, the moment of truth. After those 12 weeks of dedicated, controlled stretching, what did they find? Where does it get interesting? Let's start with flexibility, the DFROM.
Okay, yeah, this is where the results really start to pop. And frankly, it's quite surprising. The headline finding, DFROM, that ankle flexibility, significantly increased in both legs.
Both, even the one that wasn't doing the stretching.
Even the non-intervention contralateral leg.
Yeah.
Yes. And it wasn't just a tiny change.
Okay, tell me more. How much?
In the leg that actually did the dynamic stretching, the DS leg flexibility, saw a really large increase. It went from an average of about 8.7 degrees before the study up to 14.4 degrees after.
Wow, that's a jump of over 5 degrees.
Yeah, 5.7 degrees on average. Statistically, that's a large effect size. Very noticeable improvement.
Okay, that makes sense. You stretch it, it gets more flexible. But the other leg...
Here's the kicker. The non-intervention leg, the control leg that didn't do any stretching, it also showed a significant increase in flexibility. It went from the same baseline, around 8.7 degrees up to 11.8 degrees.
So it gained about 3 degrees just by existing while the other leg stretched.
Pretty much.
Rematch.
An average gain of 3.1 degrees. Still a statistically significant moderate effect size.
That is wild. That's that cross-education effect, clear as day, but for flexibility.
Exactly. It powerfully demonstrates that phenomenon. Stretching one side clearly benefited the other side's range of motion.
Okay, mine's slightly blown already. Flexibility up in both legs. But you mentioned they also measured muscle stiffness. If the non-stretched leg didn't do anything physical, did its muscle stiffness also change? Or was that different?
This is where the study gives us a crucial clue about the how. When they looked at muscle stiffness using that shear wave elastography on the gastrocnemius,
Yeah.
they found that stiffness significantly decreased only in the DS leg, the one that was actually stretched.
Only in the stretched leg.
Only in the stretched leg. The change was quite clear, especially when measured with the ankle already bent upwards a bit, at 10 degrees dorsiflexion. Again, a large effect size, meaning the muscle physically became less stiff.
But the other leg, the control leg.
Crucially, no significant change in muscle stiffness was observed in that non-intervention leg.
Okay, hold on. That's huge.
It really is.
So flexibility went up in both, but the physical property of the muscle, its stiffness, only changed in the one that was directly worked on.
Exactly. It strongly suggests that the mechanical changes, the actual physical alteration of the muscle tissue making it less rigid, happened only in the limb that underwent the stretching.
Which means the flexibility gain in the other leg must have happened through a different mechanism, right? Not a physical change in the muscle itself.
Precisely. It points away from a mechanical explanation for the contralateral effect and towards something else entirely.
Wow. Okay, that distinction is absolutely key. Direct stretching changes the muscle physically. The indirect effect doesn't. Sets the stage nicely for the why. But before we get there, one more result. Muscle strength. Did all that dynamic work make them stronger in either leg?
Right, the strength quotient. People often wonder if stretching builds strength.
Yeah.
Well, when the researchers looked at the ankle plantar flexion strength, both the rate of torque development, RTD, and the isokinetic strength, the findings were really clear-cut. No significant changes were found in any of those strength measures.
None at all.
None that reached statistical significance. Not in the stretch leg and not in the non-intervention leg either.
So flexibility up, stiffness down in one leg, but strength stayed the same everywhere.
That's the gist of it. The 12 weeks of this specific dynamic stretching improved flexibility bilaterally and reduced stiffness unilaterally, but it didn't impact strength measures in this group.
Fascinating. Okay, so if we pull all those pieces together, what's the sort of main takeaway message from these results?
Well, if you synthesize it all, the study basically shows that this 12-week dynamic stretching program is definitely effective at reducing muscle stiffness and boosting joint flexibility in the leg doing the work.
Right.
And importantly, it does that without messing with muscle strength, which is good.
Yeah.
But the really compelling part, the aha moment, is that this same program also enhances flexibility in the other leg, the contralateral one.
Without changing its stiffness or its strength.
Exactly. It really highlights this kind of systemic adaptation where working one part influences another, likely through pathways beyond just local muscle changes.
So what does this all mean for us, for you listening? Practically speaking, why did these specific changes happen? Especially that flexibility boost in the leg that did nothing? It's still kind of mind-bending. Let's really unpack the why.
Absolutely. Let's dig into the proposed mechanisms. For the intervention leg, the one that's stretched, the flexibility improvement seems to be down to two main things working together. One is that clear, measured reduction in muscle stiffness in the calf muscle. The tissue itself physically became more compliant, less resistant.
The mechanical change.
Right. But it's also very likely due to neurophysiological factors. Things like an increased tolerance to the sensation of stretching.
So your brain just gets more okay with the feeling, lets you go further?
Pretty much. The nervous system dials back its protective tension signals, allowing for a greater range of motion. It's not just the muscle getting looser, it's the neural control changing too.
And this study suggests 12 weeks is long enough for both the physical and neural changes.
It seems so. It implies that this duration allows those actual physical stiffness changes in the muscle tissue to happen, which shorter studies, maybe just a few weeks, might not capture. They might only see the initial neural adaptations.
Okay, that makes sense for the stretched leg. But the contralateral leg, this is the really cool part. Stiffness didn't change there, so why did it get more flexible?
This is where it points overwhelmingly towards purely neurophysiological adaptations. The changes are happening primarily within the nervous system, not in the muscle's physical structure.
So it's all happening like upstairs,
Yeah.
in the brain and spinal cord.
Largely, yes. Think of it as your nervous system learning or adapting globally. It could be that increased stretch tolerance we mentioned. Maybe the brain just decides, okay, this range of motion is safe now, and applies that understanding more broadly.
Like updating its safety protocols.
Kind of. Or it could involve changes in neural inhibition or excitation to the muscles on both sides. Maybe the stretching stimulus on one side triggers a central nervous system response that reduces resting muscle tone or protective reflexes slightly in both limbs.
So the brain essentially tells the muscles on the unstretched side to relax a bit more, allowing more movement.
That's a likely contributor, yes. It's a systemic neural effect.
And how does this connect to other research? Is this cross-education thing seen elsewhere?
Oh, absolutely. This kind of neural crosstalk is well documented in strength training. Train one arm and the other untrained arm often gets stronger too, purely through neural mechanisms.
Right, I've heard that.
And similar contralateral effects have been seen with long-term static stretching in some studies as well. So this finding fits into a broader pattern of our body's amazing neural adaptability. The central nervous system plays a huge role in modulating not just strength, but flexibility too, and it can share those adaptations across the body's midline.
It's like the brain learns to be more flexible, and that lesson gets shared. That's incredible. A
Yeah.
brain hack for flexibility.
You can kind of think of it that way, yeah.
So sticking with the why no strength changes then, even in the stretched leg, they worked those muscles quite a bit over 12 weeks.
That's an excellent point, and it really highlights the principle of training specificity. The fact that strength didn't improve suggests that this particular dynamic stretching protocol, while great for flexibility and stiffness, just didn't provide enough of a stimulus to actually trigger strength gains in these active young adults.
The intensity or type of contraction wasn't enough.
Likely, yes. The muscle contractions involved in these stretches probably weren't challenging enough from a force production standpoint to cause the muscles to adapt by getting stronger or more powerful.
Unlike, say, lifting heavy weights or doing plyometrics.
Exactly. Those provide a much stronger stimulus for strength adaptation. It also tells us that even some high-intensity static stretching protocols, maybe those involving active contractions, might impact strength differently. But for this specific dynamic routine, the threshold for strength improvement wasn't met.
Which also explains why you wouldn't see strength gains cross over either. If the direct stimulus isn't there, the indirect effect won't be either.
Precisely. It underscores that flexibility and strength are distinct qualities, and you need specific types of training to improve each one.
That makes a lot of sense. Okay, so bringing it back to you, the listener, thinking about your own workouts, maybe recovery, or just daily movement, what are the big practical takeaways here?
I think there are a couple of really significant implications. First, and most straightforward, if your goal is improving flexibility, consistent dynamic stretching over several weeks is clearly effective. It works.
Check. Good to know.
Second, and maybe more exciting, is that cross-education effect for flexibility. This is potentially a game changer.
How so?
Well, imagine you're dealing with an injury. Say you've sprained your left ankle and can't really move it or stretch it much.
Right. Common scenario.
This research suggests that by actively, consistently stretching your healthy right ankle, you might actually help maintain or potentially even improve flexibility in the injured left ankle.
Wow, just by working the good side.
Through these neural pathways, yes. It could be incredibly valuable in rehab settings, helping to combat stiffness and loss of motion in a limb that's immobilized or painful to move directly.
That can make a huge difference in recovery.
Huge. And think beyond injury, too. What about athletes in unilateral sports, like a tennis player or a pitcher? They heavily use one side.
Yeah, imbalances are common.
Could intentionally focusing dynamic stretching on their dominant side actually help maintain better flexibility and balance on their non-dominant side, indirectly? This study suggests it might.
A more holistic approach, thinking about the whole system.
Exactly. It encourages us to think about how interconnected our bodies are, and that flexibility isn't just about the local tissue, it's also heavily influenced by our nervous system's overall state.
Those are really practical and thought-provoking applications. It definitely shifts perspective. Now, every study has its limits, right? What were some limitations here, and what's next for research?
Absolutely. Good science always leads to more questions. The researchers themselves pointed out a few things. For one, they didn't use surface EMG.
Electromyography, measuring muscle electrical activity.
Right, so we don't know the exact level of muscle activation during the stretches. That could have provided more insight into the neural drive. Also, this focused only on the ankle plantar flexors. Would we see the same effects in bigger muscle groups like hamstrings or hip flexors? Maybe, maybe not. How the effect transmits across larger joints or the trunk might be different.
Fair point. What else?
And of course, the participants were all healthy, active young adults.
Right.
So we need to be cautious about generalizing these exact findings to, say, children or older adults or maybe elite athletes who might respond differently.
Different populations might need different approaches.
Potentially. Which leads to the future research questions, really. How can we best use this knowledge? How can we harness these neurophysiological adaptations for optimal results in training or rehab across different people and different muscles?
Can we design programs to specifically target and maximize this brain-level flexibility?
That's the exciting challenge, isn't it? Finding ways to leverage these systemic neural effects for better movement and recovery.
Definitely a thought-provoking path forward. Okay, so let's just quickly recap the core findings of this deep dive.
That's good.
We learned that a 12-week dynamic stretching program for your ankles can impressively boost flexibility, not just in the leg you stretch, but also, quite remarkably, in your other non-stretched leg.
Right, that bilateral improvement.
It also reduces muscle stiffness, makes the muscle physically less rigid, but, and this is key, only in the leg that actually did the stretching.
The mechanical change was local.
Exactly. And all of this happened without any significant change in muscle strength in either leg for this group.
A very specific set of adaptations.
Which leads to a final thought for you to ponder.
Given that our bodies show this amazing capacity for cross-education, of flexibility, driven by these neural adaptations, what does that really imply for how you approach your own training, your rehab, if needed, or even just your daily movement?
Yeah.
Could there be smarter, maybe more efficient ways to reach your flexibility goals by deliberately tapping into these systemic whole-body effects that start in the nervous system? Something to think about.
Definitely something to chew on. If you're as fascinated by these findings as we are, and you want to get into the nitty-gritty scientific details,
Which are quite interesting.
we absolutely encourage you to read the full article. Again, it's titled Effect of 12-Week Dynamic Stretching of Ankle Plantar Flexors on Joint Flexibility and Musculoskeletal Properties in the Contralateral Muscle.
By Ikeda, Hiratsuka, and Isaka in the Journal of Sports Science and Medicine.
You'll find all the specific data, the methodology, everything there.
Yeah.
And of course, if you found this deep dive valuable and you want to keep exploring the cutting edge of research with us,
We hope you do.
please make sure to follow our channel and maybe turn on those notifications so you don't miss our next exploration into fascinating new